Hello everybody. In this video, we'll learn the steps involved in hypothesis testing. If you haven't already seen it, please check out the video on the graphical intuition behind hypothesis testing, and then you'll be able to follow these steps very easily. The first step is to set up the hypotheses, the null and the alternative, and check conditions, particularly to check whether we could use the central limit theorem to get the sampling distribution of x bar. The second step is to decide on our level of significance, or alpha. Now, alpha is the threshold probability that we are willing to, is the threshold probability for us to deem an event to be extremely unlikely or likely, and it will help us figure out whether we're rejecting the null or not. The convention is to set alpha at 5%, but alpha could also be set at 1% levels or 10%, but we'll mostly say 5%. The next step is to compute something called the test statistic. Now, the test statistic is actually nothing but where if we're trying to compare x bar with the hypothesized population in mu naught, the equivalent of comparing the equivalent way of doing the same comparison is to convert the specific x bar value into its z-score or t-score, as the case may be. And we'll use that score and compare that against 0. And that is in principle what the statistic is. So you take your x bar and you either divide it, you either compute a statistic which looks like this or another one which looks like this, depending on the case maybe. Here x bar is the specific value of sample average in your particular case. Okay? That's the third step. The fourth step is to identify the rejection region, and we'll identify this. We'll either find the rejection region or something called the p-value, and we'll spend some time on this. Rejection region will be determined by the level of alpha you decide, and it will also be determined whether your hypothesis is two-sided or one-sided, the alternative. So that's step 4. And the next step is to make a decision about the null based on the information we're gathering from steps 3 and 4, and then finally state an overall conclusion. So let's go through these steps in detail. Now, in this course, we're only going to be focusing on the case where we are hypothesizing about this population mean, and we're using the sample mean as a point estimator for that. And we are figuring out whether we can gauge about mu from our x bar value. So that's the case we are dealing with in this particular course. So step 1, we set up the hypotheses. We're only dealing with a single average x bar, and where this process is referred to as a t-test hypothesis. And the t-test comes from the fact that usually we won't know sigma, so we'll use S instead. We'll use the t distribution, and therefore this entire process is called a t-test of a hypothesis test is called a t-test. So let's set up the hypotheses. When we have a two-sided hypothesis, the null will be mu equals some number. The alternative is that mu is not equal to that number. That's a two-sided hypothesis. We could also have a one-sided hypothesis. We'll have a left tail hypothesis if the alternative says that the mu is lesser than a specific number. We'll have a right tail hypothesis if the alternative says that the mu is greater than a specific hypothesized number. And specifying this, you'll be able to write this down based on how the problem outlines the problem, and we look at some examples. So we first determine if it's left tail, right tail, or a two-sided test. And then we check for conditions to see whether we could use our central limit theorem. So the conditions are the data either comes from an approximately normal population, or the sample size is greater than or equal to 30, or as long as even if the population size is less than 30, if there is information that tells you that your population is fairly smooth and there are no outliers, we'll still go ahead and use the central limit theorem. For the purposes of this course, don't worry too much about whether CLT is satisfied or not. We'll just go with the assumption that CLT can be used. So that's the first step. Second, we decide on the level of alpha. Alpha is usually 5%, so we take it to be 0.05. If alpha is not specified, go ahead and just use the 5% measure and define alpha. The third step is to calculate what I told you as the test statistic. Now, whenever sigma is known, the test statistic is written down as Z star, and it is just computed by x bar minus mu naught by sigma by root n. And this x bar is your specific sample average. When sigma is unknown, we use a T star value, where it is x bar minus mu naught by S over root n, and x bar is the specific sample average, S is the sample standard deviation, N is your sample size. Now this T star will follow a T distribution with N minus 1 degrees of freedom. Meaning we'll use the T distribution with N minus 1 degrees of freedom to compute our critical threshold values. So step 3 is to get the test statistic. Step 4 is what we'll spend some time on. And there are two ways of going about doing step 4. There's something called the rejection region approach and something called the p-value approach. So that's step 4. So let's learn about step 4 in the rejection region approach. Now we've identified our test statistic. So we're going to look at scenarios where we're only using the T distribution, because oftentimes we don't know what sigma is. So we'll only end up using sample standard deviation. Therefore, a T star as test statistic is more appropriate. So we'll learn that. Now I have to find something called the critical values. And these are actually your threshold values. Let's look at an example. Let's start off with the two-tailed hypothesis test, where the null is that mu is equal to mu naught, some hypothesized value for the population mean. The alternative is that I'm saying mu is not equal to mu naught. So if this is my x bar and if mu naught is right here, mu naught equal to mu naught could be that, maybe I'm saying that mu naught is greater, my population mean is greater than this value or lesser than this value. And it could go either directions, and therefore we'll be calling this a two-tailed test. Now, we already have our test statistic defined. And suppose we say alpha is equal to 5%, then I'm going to focus on those areas where the probability of finding a specific number is 5% or lesser. I'm trying to identify the region where I'll end up saying that this specific value that I'm seeing is too different from my hypothesized value. When will it be too different? When there's a very, very small probability of getting that specific value. So we're going to look at regions where there's a very small likelihood of a particular value showing up. Now, if we set our threshold to be alpha equals 5%, we're saying that, 95% of the values have to be within a specific interval. If for 95% of the cases, I won't reject the null, but only for 5% of extreme values, I reject the null. Now, when I have a two-tailed hypothesis, my extreme values could be greater than mu naught or lesser than mu naught. So this 5%, I'm going to divide it equally between the right tail and the left tail. And I'm going to divide it in such a way that the area to the right of the specific threshold is about 5% by 2 or 2.5%. And the area to the left of a specific threshold is 5% by 2 or 2.5%. So this region that I've shaded in red, I'm going to call that my rejection region. Because values in either of these tails have a very, very small probability of showing up. And therefore, if I end up getting a test statistic, okay, so here instead of mu naught, I'm going to put this as 0, and I'm going to call this a T distribution. Okay, so this is T alpha by 2. This is minus T alpha by 2, where it is T alpha by 2 tells me that the area to the right is equal to alpha by 2. Here, by symmetry, I can identify that this is minus T alpha by 2 such that area here is also alpha by 2. Now, in these two regions, the probability of finding an extremely unlikely event is very, very small. So if my T statistic ends up falling here or here, it falls in the rejection region. meaning the specific t-score that I've gotten for my hypothesis is greater than this threshold value that I'm setting. So essentially, between these two threshold values, 95% of the cases are accommodated. Only 5% values are left. And if I compute a t star value, which falls in one of these, 5% regions, then that tells me that I have evidence to reject the null hypothesis. Therefore, I'll reject my H naught if my t star is greater than t alpha by 2, or if my t star is lesser than minus t alpha by 2, because in both those cases, it falls into the rejection region. So if your value falls in the rejection region, you reject them. And the critical value here is given by these 2 points. So these 2 points are my critical values, because they help me delineate the threshold where, if beyond that threshold, I deem an event to be extremely unlikely. So that's my critical value. So this is how we do a hypothesis test for a two-sided hypothesis. And from the previous video, I would have told you where this t star statistic comes from. Essentially, you are going from any normal distribution to its standardized version. And that's where you get this t statistic. So this is the way for a two-sided hypothesis test. When you look at a right tail test, that is where your mu is greater than mu naught in the alternative. So you're going to set a threshold level of, say, 5% here again. And I'm going to look at events that are 5% or less likely to happen. I'm trying to label my unlikely events. And if my center is here, I'm going to look at events if mu is greater than mu naught, I'm going to be focusing on this part of the distribution. And I want to identify regions which have a very low probability, because I want to find, if my test statistic is falling in that region, which has a very low probability associated with it. Here, I'll choose my critical value as T alpha, such that area to the right of this is 5% or alpha percent. Because I'm only interested in one part of the tail, because my alternative hypothesis is designed that way. And I'll define my T statistic in the same way. Okay. And I'll say that if my T star falls here, anywhere in this region, it falls in the rejection region, and therefore I should reject my null. So reject H naught, T star is greater than T alpha. And that's how you identify the rejection region for a right tail hypothesis test. Similarly, for a left tail test, we'll do it the other way around. Left tail test is where my alternative is that mu is lesser than mu naught. So I'm going to be focusing on this part to the left of the center. And I want to identify the region which has a very low probability associated with it. So I'll focus on the left tail, which has a 5% probability or lesser. And if I, if I say that this area is equal to alpha, say 5%, if we go with the same alpha here as well, this region is 5%, and this point is actually minus T alpha. It comes from symmetry, okay? And if my test statistic happens to fall in this region, anywhere in this region, I'll say reject the null. Reject null if T star is lesser than or equal to minus T alpha. And that's all the rule there is to figuring out whether you should reject the null or not reject the null. So first step is to identify whether you have a two-tailed or a one-tailed test. And depending on whether you have a two-tailed or a one-tailed test, you'll identify your rejection regions. The rejection regions will all be, the areas of the curve such that the area to the beyond that point is equal to your threshold probability. If it's a one-tailed test, it's easy to identify those threshold regions. If it's a two-tailed test, what you do is you identify your threshold probability, divide that by 2, and find that area equally on both tails. These will be your rejection regions. And all of these rejection regions lie on the T distribution. So if you find a T statistic which happens to lie in this rejection region, go ahead and reject the null hypothesis. That is all the process there is to using the rejection region approach. A very related approach is called the p-value approach. I'll do that in a separate video. Now, for the last two steps here are that you make a decision about the null. If the test statistic falls in the rejection region, you reject the null and you conclude that the alternative is true. If your test statistic does not fall in the rejection region, then you don't have enough evidence to reject the null. So if your test statistic happens to fall anywhere here in this case, or anywhere here in this case, or anywhere here, then there is no evidence to suggest that, I mean, all of those suggest that there's a good chance, there's a good level of probability associated with getting a T-stat value there, and therefore it is not an unlikely event. So there is no evidence to reject the null. So the bottom line is, if you find your T statistic falling into the rejection regions, reject your null. If not, do not reject. And then the overall conclusion is that if you happen to reject your null, there is enough evidence to say that there is a statistically significant effect here, that your sample mean is not equal to the, there's enough evidence from the sample to conclude that the population mean is not equal to mean naught. And this, there is statistically a significant effect, which is leading us to say that they're rejecting the null. So that's how you conduct a hypothesis test. In the next video, I'll take you through the p-value approach. And I'll also tell you how this whole hypothesis testing process is very closely related to how we define confidence intervals. And that should give you a pretty good sense of hypothesis testing. So I'll see you there.